So, today we are going to start our last lecture or the fifth lecture of the first week, and here we are going to introduce what is called a cross product of two vectors. That is, I will define a new kind of multiplication of two vectors, and I will call this as a C vector. It is a new so this product of two vectors does not give me a number just like the dot product, it gives me a vector. So, let us see what do we mean by this, and let us from practical perspective also we will see what happens. So, here is the XYZ plane, space. So, if A is a one vector here and so B is another vector in space. Now, C is the cross product of two vectors is a vector which is if you write A cross B, then C vector, when you write A cross B, you move from A towards B, and then in the plane formed by the vectors A and B, the C vector or the dot product or the cross product is perpendicular to the plane in which the vectors A and B are lying. So, why did I draw C in this direction and not the other direction? So, it is like moving screw. If you take a screw and put it in front of your nose straight, and if you try to rotate it in the counterclockwise direction, counterclockwise from your point of view. Now, if I am rotating it in front of me, it is counterclockwise from my point of view, but it is clockwise from your point of view. So, from my point of view, if I move it in a counterclockwise direction, you will see the nose of the or the tip of the nail or the screw will just point towards my nose. So, that is exactly what is happening. So, if I from here A to B, when I am moving it from A to B, the tip is moving towards this direction. So, I am just going to demonstrate to you through kind of experiment here. So, it is kind of here like this, and suppose I am moving it like this. You see what happened is that, so this is how a screw is moved. So, this is a screw and I am with a screwdriver, I am moving it from, suppose there are two vectors which we are defining the plane in which this face of the screw is lying, and I am moving it like this. Then I am actually putting the screw, I am moving it like this. So, you see that it is, the bottle is going, if it is clockwise, right. So, this is the screw which you have got and you are moving it. So, this is a screw that you want to put in, right, and you are moving in this direction clockwise from your direction, then see what is happening, the screw is getting inside. So, basically clockwise. So, if I was standing there, then from me it would appear that I was putting it counterclockwise and it was going inside like this. So, in this case maybe I am little mistaken, I think I have to, this case it might be, if I am moving from A to B, then I would see from my side it is coming to the counter, it is going on the clockwise direction. So, C should be something like this. Okay. So, how do you define this vector? So, there is a way of defining this vector. So, we will have a way. So, we will take A vector as A1 I vector, where A1, A2, A3 are coordinates of A. So, we are just in 3 dimension now, because beyond 3 dimension you cannot define the cross product, but 3 dimensional ideas would actually be helpful in the sciences, in natural sciences like physics, and you will very soon see their applications towards the end of the course. When we talk about Green's theorem and Gauss divergence theorem, Stokes theorem, you will see how important these concept of A cross B is, and a large amount of electromagnetic theory which combines the forces of electricity and magnetism into one framework, which Maxwell did, also needs this kind of operation. So, this is what it is, and B vector. So, the coordinates are b1, b2, b3. So, I can represent it as b1 I vector, b2 j vector plus b3 k vector. Those who know linear algebra, you know this is nothing but expansion through the standard basis, which is I, j and k, which is 1 0 0 0 0 1 and 1 0 0 0 1 0 and 0 0 1. So, I am not getting into all these details, you know these things very well, pretty well. We have been writing this for quite some time now. Now, let me tell you how do I define it. Now, how do I define it? What is A cross B? This is a very strange kind of definition where you will see that we am talking about a determinant. I am talking about a kind of determinant. I want you to compute the determinant where one of the rows consists of these I, j, k vectors, I, j, k. You might say, oh, how can you do it, because determinant you always put in some numbers. How are you suddenly telling, oh my god, this has to be something like this, this has to be this is a metric, and how many, these are all vectors, how can you compute the determinant? Of course, I can say, okay, you can write down this whole thing in terms of the 3 vectors and then do the determinant, right. Then you will also get the same answer. But okay, we will not get into the details. So, how can I write this? So, what I am writing, what are the components of A and B with the I vector? A1, B1, here A2, B2 with the J vector and with the K vector. So, this is the definition. So, you might ask how this definition is meaningful, because I, J, K are vectors and not numbers, but I can say I can write down them as numbers as 1 0 0 0 1 0 and 0 0 1, and then I would like to write the expand it in the form of determinant, then also you will get back the same kind of stuff. So, let me just expand the determinant and let me just see how can we write it. So, what did we have here is that for 2 vectors A cross B, so computing determinant is the same. It is not that I am doing something, it will look like exactly the same. So, it will be the same thing here, but I will write it in a slightly different way. So, this will be a real number if you take the determinant of this, which will be scalar multiplied, would make a scalar multiplication with this vector. So, it will be A1, A3, because if I take I, then I take off this first row and first column. So, sorry, A2, A3, B2, B3, this multiplied by I vector. Now, minus sign would come just like in ordinary determinant. Now, I will have A1, A3, B1, B3 plus this, which is multiplied with a J vector, and A1, A2 and B1, B2 is multiplied with the K vector. So, that is what is how you define the cross product, okay. And what let us now look into, again as I showed you through this, that okay, if this is A and this is B, and if I am rotating from A to B in a clockwise fashion, the C vector is in this direction, and if I rotate it in an anti-clockwise fashion, the C vector, as I told you just before with a screw I am showing this example, if I am rotating in an anti-clockwise fashion, anti-clockwise towards me, then you see that this nose of the bottle is coming towards me. So, this is what it does. There is a very important kind of stuff that you really need to know before you do anything with this. We need to put certain properties of these vectors into perspective. So, let us put some properties. So, number one property is that if I have A cross B, these two, this is the negative of B cross A, because the directions will change, because here it is a vector, it has both magnitude and direction. So, we have not computed the magnitude of A cross B. What is the magnitude of A cross B? We will soon do that. And you have, suppose now I will distribute, it is like it follows a kind of similar laws of arithmetic, that if I distribute this cross product over the addition of two vectors, that is A cross gamma B plus mu, these are real numbers of C vectors, scalar multiply. So, this is nothing but gamma of A cross B plus mu of, sorry, not gamma, gamma is a real number, A cross C. So, this is what you will have, this is a property. So, distribution of multiplication over addition. So, again distribution kind of the reverse kind of thing means basically you have multiplied from this side, you can multiply it from the other side also. So, I would not do it. Suppose you have gamma A vector plus mu B vector, and this you have multiplied with C vector, you can easily write down what will be the answer. I leave this to you. But what you get from this is the following, that if you know this property, then let us look at the first property. What does it say if I put B is equal to A? So, if I put B is equal to the A vector, it tells me immediately that A cross A vector is same as the negative of A cross A vector, which similarly shows that twice of A cross A vector is 0, which immediately again shows. See, this is simple, any vector which is equal to its negative must be the 0 vector, it cannot be otherwise. Okay. So, this is an interesting property. Once you have known this property, you can play around a bit with I and j. So, let us write down what you will have. Now, let us look at the 3-dimensional picture again with ij vectors in tau. Do not mind my drawing. So, this is the x axis, y axis and z axis, and this is the I vector with coordinate 0 0 1, sorry 1 0 0, and this is a j vector with coordinate 0 1 0, and this is a k vector with coordinate 0 0 1. Now, one thing is clear from the very beginning, that I cross I is equal to j cross j is equal to k cross k, that must be 0 from what we had just discussed. Now, what is I cross j? That is, if I move I towards I from j. So, basically if I am looking from this side, I and j is in the xy plane. If I am looking from this side and I am moving I to j, right. So, from my side I am looking at it. So, I am if the observer is standing along the z axis, his eye is along the z axis, then he observes that the eye moves towards j in a counterclockwise fashion, so that the screw will move towards him along the z axis. That is, if his eye is on the z axis, it is the k vector which will move towards him. So, I cross j is the k vector. Similarly, if I have j cross k, so again if my eye is on the x axis and if I move the vector from j to k, if I rotate from j towards k side, then I am rotating the whole system in an anticlockwise direction. So, the I vector will move towards me. So, I will have j cross k as I vector and I will have k cross I as j vector. This is a beautiful simple setup. I think this is something you should always remember, because this can be used in many places. Now I will talk about something called a triple product, okay, a triple product, and we will see what a triple product is. A triple product of two vectors is that you take the dot cross product of two vectors and take the dot with the third vector. So, this is called the triple product. This triple product is a very useful one, as you will see very soon. Triple product. So, you have three vectors given to you, A, B and C, and where A vector as before is given as A1 I vector, A2 j vector and A3 k vector, while B is again given in the similar fashion, I think, which I should not repeat. B is given as B1 I vector, but still I am doing it for the sake of clarity, I guess. And C is C1 I vector, C2 j vector and C3 k vector. So, triple product is this, the triple product is defined as follows. Triple product is A cross B intersections is a dot product with C. So, I take the cross product of the two vectors and take a dot product with C. Now, if I expand it, so what I will get? I will get the following. So, I will get, so triple product is A2 A3 B2 B3 I vector minus A1 A3 B1 B3 j vector plus A1 A2 B1 B2 as k vector, and this dot product into C1 I vector, C2 j vector and C3 k vector. If you recall the definition of the dot product which we had already given, so then this is nothing but, so this whole triple product I am writing it here so that you can see it clearly. So, this is nothing but C1 into the determinant of A1, A3, B1, B3 minus C2 into the determinant of A1, A2, B1, A1, A3, B1, B3 plus C3 into the determinant of A1, A2, B1, B2. So, it can be written either as a determinant whose first row is C1, C2, C1, C2, C3, just this has to be a correction, sorry, it's A, this is A C1, so it's A2, A3 and B2, B3. So, if you look at the, so what I did, the dot product, the first component of this, first coordinate of this with the first coordinate of this and second coordinate with second coordinate, third coordinate with third coordinate and sum up. Now, if you look at this thing, this can be either written as a determinant with the first rows as C1, C2, C3, or it can be written as a determinant as a third row as C1, C2, C3, because the sign convention of the first row and third row are the same. So, actually the determinant, if you just try to remind you, that is the determinant if I have 9 positions. So, you can start expanding from any of the rows. So, then if you go by the rows, in plus minus plus minus plus minus plus minus plus. This is the way the convention is carried out. So, just keep this in mind, and so if you do that for our convenience, just for writing convenience, I am writing it as a determinant which is expanded with C1, C2, C3 in the third row. Sorry, A1, A2, A3, B1, B2, B3, C1, C2, C3. So, what do you get? So, what I get is that naturally, because A dot B, A cross B is a vector and C is a vector, so the dot product of two vectors is a scalar, but the scalar can be expressed as a determinant with the inputs which are the coordinates of the vectors A1 and A2 and A3, and this will become pretty important as we go along this concept. Now, I want to find the area, I want to find the magnitude, the length. So, my question is, what is the length of A cross B? Magnitude. What is the length or the magnitude, or just slight length, which is much colloquially easier. Length of A cross B. In some sense, I am asking you to determine the norm of A cross B. And so, what is that norm of A cross B? That is essentially, that is exactly what I am trying to ask you. Okay. Now, how do I do it? I have to first note that A cross B is nothing but a vector whose coordinates are this, this and this, which are determinant. So, if I write it as a square, the norm square is then square of the value of this determinant, square of the value of this determinant, square of the value of this determinant, which means if I go back and write it down, the first determinant is A2 B3 minus B2 A3 whole square plus A1 B3 minus B1 A3 whole square plus A1 B2 B1 A2, A1 B2 minus B1 A2 whole square. Now, this is the length, the square of the length, and now I will write it in slightly a modified way. I will just I will square up these, I will make a square and then rearrange the terms, and then I will get the following expression, which I am just writing it down. I ask you to check it. So, from here to here, your job is to take a cup of tea and sit down and do the check. So, the checking, if that will give me A1 square, A2 square, A3 square into B1 square plus B2 square plus B3 square minus A1 B1 plus A2 B2 plus A3 B3 square. So, this is a very quite cumbersome computation, and just I have been lazy, and just because of the time constraint I am leaving out this computation and asking you to check this computation. And then what happens if I go back, please understand that A is a vector with A1, A2, A3 as coordinates, and B is a vector with B1, B2, B3 as coordinates, and you can understand this term A1, B1, A2, B2, A3, B3 is just the dot product. So, I can write this whole thing as norm A square, norm B square minus A dot B, of course I should have the arrows on the top, whole square. So, this can be written as norm A square. So, if I have the two vectors A and B and theta be the angle between them, and I can write this as this square minus norm A norm B cosine of theta, where theta is the angle between two of them. So, this will give me that norm A cross B whole square is norm A square into norm B square minus norm A square into norm B square cosine square of theta. And as a result of this, I can write norm of A square into norm of B square, which we can take out from the expression, from the bracket. This is again the distributive law, multiplication over addition, standard distributive law of arithmetic. So, every time we are actually doing this sort of computation, which looks very common and very obvious to us, we are actually doing a very deep operation. We are actually writing down certain kind of laws of arithmetic, which was initially written down because they were figured out to be true with numbers, with natural numbers, and then it was written down as a law that a number which if it has to a real number, it has to follow all these things. So, they do follow, right. So, this is not just, if on the top of it, it looks like it's just an obvious operation, but it is not so very simple as we think. This is a kind of axiom, kind of thing which actually happens. So, we put it as a kind of law which we always have to remember and follow, that this is nothing but distribution of multiplication over addition. The kind of laws I had written down there. So, this is nothing. If you just think that these are real numbers, then this is just multiplication and this is just addition. That is exactly what it is here. So, those who know trigonometry would immediately realize that sin square theta plus cos square theta is 1, and so as a result of which, sorry, I have to put A and B here. The arrows, I always seem to forget the arrows. No, so I will have here sin square of theta. So, noting that length is always positive, I will simply have this equal to A, B, norm of A, norm of B, sine of theta. There is a deeper geometric meaning of this, and that is what I am going to work out here on the board, that what does this thing actually means, what does cross product mean geometrically. And you will be surprised to know that geometrically the cross product simply means the area, and that is what we are going to do. Will show that the area of the rectangle contained by the, or the parallelogram, sorry, not rectangle, parallelogram contained by the vectors A and B is nothing but the cross product A cross B, and that is what we are going to demonstrate, but I am looking for a duster. Okay. So, with a duster here, let me try to demonstrate this. Some time is usually lost when I am rubbing the board, but that is how life is, that is how things are done in the class. I sit here before an imaginary audience and I am speaking to you as if I am giving a lecture before you in reality. So, let me now write down what that stuff is. So, suppose in the 3-dimensional space, here is my A, this is the origin, right, and here is B. Maybe I should make it, so here is your, maybe the angle I should make it, it might immediately in the space it might look as if I have drawn something perpendicular, I maybe actually not, I should write it like this. So, this is my A vector, this is the origin, and this is a B vector. So, let us make out a parallelogram out of it. So, maybe something, so it is parallel to this. And something which is parallel to this. So, this is a parallelogram. Now, what I am trying to claim is that A cross B represents the norm of A cross B that you see here, actually represents the area of the parallelogram contained made by these vectors A cross B in the plane that contains the vectors A cross B. Because how do you compute the area of a parallelogram in a plane? Suppose here is the area of the parallelogram, see this is one. So what do you do? Area of a parallelogram, how it is computed? How does one compute the area of a parallelogram? So this is the height, right. So you basically compute this side, and suppose this has a length L and this has length, suppose this has a length B and this has length L and this is theta, and this line, the height H, is B sin theta. And the parallel area of the parallelogram, if you define the area, so what is the area? Suppose I have constructed this rectangle like this, and because they are between the same parallel lines, the area is same. This is what you learn in your school geometry, but though it is not so simple, we are doing things very simply, but it is not so simple. So this H equal to B sin theta is the height. Basically if you take the height, basically this part and this part, because this is also theta, and this part, so that would, so this height and this whole part, this part would make up, which is same as this. So this length and this length is same, so this whole thing is actually L. So if you look at the area of the rectangle that is formed, the area of the rectangle is L H B, sorry, L into, area of the rectangle is L into H. So rectangular area, rectangle, rect, is L into H, length into the breadth, but that is what is L into, what is H? It is B sin theta. So you observe that this length, this line, this side of the rectangle must match this side of the rectangle, but this line is same as L because this is a parallelogram, opposite sides are equal. So this length is also L, this full length, and so it is L into H is the area of the rectangle, and the area of the rectangle is equal to then LH into B sin theta, and this area of the rectangle is same as the area of the parallelogram. So if you consider this part, the length as B vector, and this is theta, and this part the length is A vector of this, and you know then what is the answer. So the area of the parallelogram, this parallelogram, this one, this one. So I am trying to find the area of this. Area of the parallelogram is nothing but norm A, norm B, the lengths into the angle between them, sine of theta. And what is it? It is nothing but the norm of A cross B. So A cross B, this vector in some way represents the area. So the vector A cross B could be either in this direction or it could be in this direction, perpendicular to the plane. It depends on which way you are rotating the A and B, A towards B or B towards A. But this vector, say A cross B or this one, whatever you want to say, whichever is A cross B, this vector is actually representing the area, and hence area itself can be thought of as a vector, the area vector, and this would be very helpful when we try to study Stokes theorem and Gauss theorem, which are extremely important in engineering and physics. So please understand that cross product gives the whole goal of cross product is to tell you that we can view the notion of area as a vector. We have always thought of area as a scalar, a number, but area can also be viewed as a vector. So, area vector of an object is actually perpendicular to the object whose area you are trying to calculate, the length of, for example, the plane, for example, the rectangular. So, the cross product of two vectors is actually the area of a rectangle. So, area of a rectangle can be also viewed as a vector, and that's where the beauty lies in this whole thing. So, let us now do two things before we finish our talk. Is let us look at the geometry of 2 by 2 determinants. Means basically I am trying to look at what is this. I am trying to look at a determinant of this form. Now, we will soon see something pretty interesting. Now, suppose this is a plane, xy plane. And you have two vectors, which is a1 and with coordinates a1, a2, and another is the vector b with coordinates b1, b2, and this is the angle theta between them. In a 3-dimensional setup, their coordinates are a1, a2, 0, b1, b2, 0. Now, if I look at the cross product of these two vectors, A cross B, then the cross product is nothing but there is no comma here, J and K, A1, A2, 0, B1, B2, 0. So, this is nothing but the determinant of A1, A2, B1, B2 to K vector. So, the parallelogram in the plane, the magnitude of the parallelogram, what is the magnitude of this vector? So, magnitude of A cross B in this particular case is nothing but, you take the magnitude on both sides, norm of the K is 1, right, this is the K vector. So, if you take the magnitude of this vector, and so now here we are looking at A cross B as if it is a 3-dimensional vector. So, I am putting A1, A2, 0, and then what I am getting, the magnitude of this is nothing but A1 B2 minus A2 B1. So, this determinant, what does it give? It gives me the area of the rectangle, area of the parallelogram formed by the vectors A and B in the 2-dimensional plane xy. So, 2-dimensional determinant, the determinant of with 2 entries is actually representing the area of a parallelogram. Similarly, I will show the determinant of with 3, when I am talking about a determinant with 3 entry, when 9 entries, basically 3 entries in row, each row, 3-dimensional determinant, then that determinant actually would then speak about the volume of a parallelepiped, because the notion of a rectangle, notion of a parallelogram, not rectangle, notion of a parallelogram in 3 dimension becomes what is called a parallelepiped, and that is what I am going to show, that the area or the value of the area of a parallelepiped which is made up of 3 sides by the vectors A, B and C are actually is nothing but the determinant of a form this, which is the cross product of 3 vectors. So, Suppose I draw a parallelepiped, right? So I am 3 dimension. So this is my origin. So let me see which way I will go drawing A vector, B vectors. So A vector, B vector, and this is my C vector. So the parallelepiped you can form like this. I am trying to draw this, but something like this. It will be something like this. So this parallelepiped, this is called a parallelepiped. So area of the parallelepiped is actually so we are showing how can we geometrically interpret the two notions that we have developed today. Okay, so let's have a so here is your A cross B. So this is your A vector and this is your B vector and this was your C vector. So A cross B has some kind of is a perpendicular to the plane, assuming that I am moving like this A cross B. This is my motion. So now what is the norm of what is if I take the dot product with C, what is that? So A cross B into C is nothing but norm A. So this angle is some psi. So norm A, sorry, it's I'm making a mistake. Norm of A plus B. It's norm of A plus B into norm of C into cosine of psi. That's what you have here, right? That's how, that is the definition of the dot product, right? But again, what is C cos phi? What is this C cos phi giving me? The C cos phi is actually this. It is this height. This is actually the height if I replace this parallelepiped with a rectangular parallelepiped standing between the same two parallel bases. So this is the height. So again if I take the base, the area of the base rectangle and multiply it by the height, then I get the area of the rectangular parallelepiped. So basically, and that rectangular parallelepiped should have by Euclid's geometry the same, though it is 3 dimensional. You can just take your vision further, you can just take a leap in the imagination and know that the rectangular parallelepiped which is standing between the same two bases and this parallelepiped must have the same area. So this thing is nothing but the area of the parallelepiped. because this is nothing but the height. So, the base, what is the area of the rectangular parallelepiped? The base area into the, not area of the parallelepiped, I am making a mistake, sorry, I think I should be correct, it is volume. So, I am 3 dimension, there is no area talking about. So, it is so volume of the parallelepiped, please forgive me, it should be volume of the parallelepiped. So, the volume of the parallelepiped is that this is nothing but the base area into the height. So, if you know to calculate the height of a rectangular parallelepiped is what? The base area into height. So, but that rectangular parallelepiped has the same area as this parallelepiped, so this slanting parallelepiped. So, volume of the parallelepiped, so this is nothing but the volume of the parallelepiped. This is the volume of the parallelepiped. And so what is happening? What is the volume of that parallelepiped? I know what is A cross B dot C. It is A1 B1 C, sorry, A1 A2 A3, B1 B2 B3 and C1 C2 C3, which I already know. Sorry. Because the triple product is nothing but this determinant. So, this 3-dimensional determinant is nothing but it represents the volume of a parallelepiped, 2-dimensional determinant represents the volume of a area of a parallelogram. So, here geometry both 3 and 2 dimensionals are linked to the notion of determinant. So, algebra and geometry are linked, and that is exactly what all mathematics is all about, that algebra is somehow geometry and geometry is algebra. Once you get a feeling about this, then you will start enjoying mathematics. Okay, so I call it off for today and we move forward for the next day's one, which will come along. It will be, we will be going now towards higher dimension. So, we will no longer be in 3 dimension, we will be in 3, 2, 4, 5, 6 up to n dimensions, and we will show by some examples why these n dimensions matter, why you have to go beyond 3 dimensions. One comes from physics, from special relativity, another comes, a very good example comes from linear programming, and that is where we are going to show that we really need to talk about dimensions more than 3. We really need to talk about something called Rn, where n could be 5, 10, 20, anything, even a million, right. So, thank you for your patience, and if there is any problem you can always write it down on the portal of the course, and please go back and listen to this lecture once again, that the core idea is that algebraic definitions and manipulations are actually inspired from geometry. Math is all about visualization. Thank you very much.